Hello everyone, I'm Paul,
I'm Emron.
And I'm Jay.
and today we'll be talking about the motion of a spool. For our first case, we'll be pulling the string straight up and see our spool spin in a clockwise motion as well as translate to the right. The motion of our spool can easily be explained by using our equilibrium equations for both our free body diagram and our mass acceleration diagram. If we take the sum of the forces in the x direction on our free body diagram and our mass acceleration diagram, we can see that our friction force on our free body diagram will be equal to ma, and we know the acceleration on our mass acceleration diagram is to the right. Therefore, we can infer that the friction force is what causes our spool to translate to the right. We then take a moment about the center of gravity on our free body diagram and our mass acceleration diagram. We notice on our free body diagram that our friction force causes a counterclockwise moment, while our applied force causes a clockwise moment. We also notice on our mass acceleration diagram that the rotational acceleration is in the clockwise direction. Therefore, we can assume that our applied force is greater than our friction force, and our applied force is what's causing our spool to rotate in the clockwise direction.
In case 2, we pull the spool straight to the left. The force from P is greater than the friction force, and the moment arm of P is smaller than the friction force F. The moment from the friction, which wants to rotate counterclockwise, is greater than the moment of the force P, which wants to rotate clockwise. So the spool rotates counterclockwise and moves into the direction of the pulling force, P.
In case 3, we pull the string in the direction of the critical angle. In this angle, the spool spins in place while it rotates at a constant angular speed with no translational motion. This happens when the force from P and the force from friction cancel out, but since the moment arm from friction is large, it causes the spool to spin in a counterclockwise motion. If we apply our equilibrium equations, we can see that our critical angle theta depends on the inverse cosine of the inner radius over the outer radius. If we get this critical angle right, the spool will rotate in place without moving any direction, which we obviously didn't get right in this video.